here we are talking about cosets. And if I have a subgroup and two elements, oops, I always do that, that two cosets are the same if and only if AB inverse belongs to H. So this is a test to see whether two cosets are the same. We know about H. H is a subgroup. And so are these two cosets the same? Well, we can just see if this element is. Let's look at some examples here. Well, here I have it. We have the following right cosets, color-coded. So now we can see whether two cosets. And so I can look and see, hey, are these two the same? Well, I can just check to see, is AB inverse in H? Well, AB inverse is going to give you 1, 2. Is 1, 2 in H? Sure it is. So these two cosets are the same, which we already knew because they're both red. Great, and we can play the same game. If I have E and B inverse, I get the same thing. Ask a different question. These two are the same, so let's ask if A is 1, 3, and 1, 2, 3, and B is equal to 1, 2, 3. Well, I see that that's equal to exactly that, which equals 1, 2, and that's an H. So 1, 2 is an H. So that means that H13 and H123 have to be the same. And we see that they actually are. Oh, and of course we get the other direction. If you want 1, 2, 3 to be A, and you want 1, 3 to be B, you can do that. So the last thing to check here is these two are going to end up, we know these two are the same coset. So I'm going to look at 2, 3, and I'm going to look at 1, 3, 2. So 2, 3 is my A, 1, 2, 3, 1, 3, 2 is my B, and I just do the it's equal to that. That boils down to that boils down to 1, 2. 1, 2 is an H. And similarly the other direction. So we see that if the cosets are the same, this calculation certainly works. So let's see. Let's suppose first that the cosets are the same, and I need to prove that AB inverse is an element of H. A's belongs to HA, but HA is equal to HB, so A is in HB is what the point is. A is in if we sum little h such that A is equal to HB, because that's what it means for A to be in HB. Well, what can we do? I can just multiply both sides by B inverse, and then I get that AB inverse is equal to H, and H is in H, so H is in H, so AB inverse is in H. That's exactly what we want. Assume the other direction now. Assume that AB inverse is in H, and we're going to show that that's true. Well, I'll do that by containment. So first of all, a typical element of HA looks like little ha for some little h. HA, I can put in an identity to allow me to insert some ABs in there, or AB inverses in there. Right, so I'm just multiplying by an element and its inverse. So I'm not changing anything. And you see that this works out to, oh, those A's are going to cancel. So I end up with exactly that. Look at that. I can rearrange it so that I write HA through some trickery, right? I threw in the identity and then I made it the identity equal to some element times its inverse. Did some algebra and I cleaned it up and I got that. It boils down to this thing, which is an H. Why is this an H? Because little h is an H, and because AB inverse is an H. So this is just a product of two things in H. And then times B, which is HB. So, which is in capital HB. So what I get is that HA has to be a subset of HB. The same thing, same to that. There. Look at that. It's exactly the same argument. So the other way, and we're done. So I get containment both ways, so we include that it works. So we get that HA equals HB if and only if AB inverse is an H. Done.